In today's fast-paced manufacturing landscape, the need for efficiency, precision, and adaptability has never been greater. Collaborative automated robots have emerged as pivotal tools in addressing these demands. Unlike traditional industrial robots that operate in isolated environments, collaborative robots are designed to work alongside human operators, enhancing productivity while maintaining safety. From a mechanical engineering perspective, collaborative robots represent a transformative solution to the challenges faced by modern manufacturing. I'm Owen Adams, fourth-year mechanical engineering student.
I'm Siva, Pragallapati, a fourth-year mechanical engineering student.
I'm Bizzak, I'm a fourth-year mechanical engineering student.
And together our team developed an automated process where two Dobot magician robots collaborated to solve a simple word puzzle. Through understanding how these robots operate together, this work helped address the problem of efficient and precise collaboration between multiple automated robots in modern manufacturing. In our first lab, we worked with a conveyor belt equipped with a motion sensor to notify the Dobot magician robot when an object was present. Upon receiving this signal, the robot used a suction-based end effector to pick up the object and move it to our designated workspace. One major challenge we faced was the robot's limited recognition capability. It could only identify the object's position along the y-axis. This meant objects had to be placed perfectly to ensure successful pickup. This challenge of requiring perfect placement in Lab 1 highlighted a key limitation in our setup, our robot's inability to fully identify object locations. In Lab 2, we addressed this issue by integrating an overhead camera with color extraction technology, enabling the robot to detect and locate objects in both X and Y coordinates. This allowed us to pinpoint the centroid of colored blocks for precise handling. With this improved recognition, the robot could accurately locate and pick up objects, moving them to designated locations with greater efficiency. This step marked significant progress in refining the system's accuracy and adaptability.
In our third lab, we focused on collaboration between two Dobot magician robots using I/O communication. To achieve this, we built a rudimentary circuit on a breadboard capable of transmitting a signal to indicate when an object was placed and ready for pickup. This required precise calibration of the pickup points for both robots, as each operated within its own unique coordinate system. Once the communication was established, we shifted to a more complex task, aligning two detected objects. The first was a card labeled Dobot, and the second was a matching hole to insert the card into. Using shell modules, we developed a short code segment to align the angles of these objects for precise placement. This process posed a significant challenge due to the end effector's rotation limit of plus or minus 135 degrees, preventing full 360-degree motion. To overcome this, we simulated various starting and ending angles, refining the code to handle these limitations effectively. Through these labs, integrating sensors, refining object recognition, establishing communication between robots, and overcoming mechanical and coding challenges, we developed a comprehensive understanding of collaborative automation. These foundational skills and techniques set the stage for our final project, where we combined everything we learned to tackle a more complex and dynamic manufacturing problem.
For our final project, we were tasked with solving a simple word puzzle using one robot to correctly identify the color and shape of the desired letters, a second robot to align these letters into their slots correctly, and I/O communication between the robots to automate the process. To accomplish this task, we first identified our general approach, consisting of sending and receiving letters one at a time, with a time delay on the sending robot between each letter sent and I/O communication to trigger the receiving robot. Next, we built code for the sending robot with our main challenge being the color and shape recognition of the blue letters. We overcame this challenge by adjusting camera settings and color extraction code. After the sending code was completed, we built an iterative code for the receiving robot to place the letters it received into the word puzzle. This code called on our previous knowledge of angle alignment in order to accurately place the letters in their corresponding slots. For our final project demonstration, we applied skills that we learned throughout all the previous labs to autonomously solve a wooden word puzzle using the two robots. The process involved two sequential tasks. In task 1, a robot identified and picked letters of a specific color using vision-guided robotics and transferred them to a designated location. We optimized color extraction code for precise letter identification and pickup. The robot then signaled the receiving team using I/O communication. In task 2, our robot retrieved the letters, aligning them with using the angle adjustment code, and then placed them into the puzzle slots with accuracy within the required 45-degree tolerance. Ultimately, the project demonstrated our mastery of collaborative automation, integrating vision processing, I/O communication, and precise robotics to address modern manufacturing challenges.